So we'll start with the I think this is summer 20 question paper 2 to just 1 second. Okay, just remember that let's start with this paper. We'll try and do this one, which is so this one is summer 20 and I said 2019, just 1 second, 1B1. Just 1 second, let me solve this problem first. 2019 winter 22. So 9701. Winter 19 and 22, just 1 second. So, and which question was this? This was question 1B1. Okay, that's actually the marking scheme. Just a second. Achha, 1. Okay, this one. I guess this question is this the question?
Yes, sir.
So this one we have to do. It's the silicon is found in many isotopes. So the isotopes are given and their relative isotopic masses are given, and the sample of silicon contains 92.2% of this, and the total percentage abundance of silicon 29 and 30 is 7.8%. So calculate. So this is, I mean, this one is 92.2%. And the rest, which is 7.8%, are these two. So if I take this as X%, so this would be 7.8 minus X%. I mean, that's what they're looking for. They want you to figure out the percentage abundance of silicon 30. But let me take that as X. So I'll just change this. I'll take this as X%. And this other one would then be 7.8 minus X%. Remember, because combined they are 7.8%. I mean, combined these two are 7.8%. So we're going to try and solve this now using the same formula, which is what is AR? It's the fractional percentage multiplied by the isotopic mass, and you're going to add all of them up. Okay, so one by one, you're going to add all of them up. Now, it's going to be the AR is already calculated. It's given as 28.09. So that's 28.09. And what you have to do is you have to, the mass 28 has 92.2%. So that's 92.2 over 100 into 28 plus. This is 7.8 minus X%. So that's 7.8 minus X divided by 100 into 29. And the last one is X% over 100 into 30. And you just have to solve for X. TK, that's the only thing that you have to do now. TK, so is that clear?
Yes, sir.
So let's go back to this question, to this paper. We'll try and do this one quickly. So 2-3, summer 2023. And just a second. Nidana, she hasn't sent them. Okay. I'll wait for them, but I'll start with this paper. So describe 2 observations for this reaction. So what happens when barium is reacted with oxygen? I mean, they're not looking for the equation, but what are the 2 things that you would observe?
So precipitate formed.
It's not going to be it's not going to be a precipitate.
Solid.
A solid is formed, a white solid specifically. Group 2 oxides are white in color.
And the green flame.
Okay, so green flame. Okay, so you're going to have a green flame. Okay, remember the flame test. Write an equation. So we've already written that down. Just hold on 1 second. That's this one. Now, calcium carbonate is converted to calcium oxide and then it's turned into calcium. Describe how the two-step process is carried out to convert calcium carbonate. So what are you going to do over here in step number 1?
Thermal decomposition.
Okay, so you're going to heat it, right? And it will decompose. So the first part is that you're going to heat it and it will decompose. So describe how and include relevant equations. So you have to include the relevant equations as well. Okay, follow the instructions very, very carefully. What's the next part that you're going to do once calcium oxide is formed?
Add water.
Okay, so you'll just add water, that's it. So describe how the two-step process is going to happen. So the next part is, the 2 marks are for the equation. You're going to add in another equation, which is water. And it's going to form calcium hydroxide. And that's about it. Okay, you're just going to describe, you're going to write heat over here and just add water in the next one. Name the type of reaction which is converted into calcium oxide. That's already somebody told us that it's thermal decomposition. Next part, state 1 common use of calcium carbonate and calcium hydroxide. What are they used in?
So to neutralize acidic soil.
Because that's the main one, neutralize acidic soils. And next one is that you've got a gray silver solid and aluminium and gallium. So again, if you have this question, so you're basically talking not about gallium, but you're actually talking about aluminium. Starting with the first one, you have to write an equation of gallium oxide when heated to form this thing. So I mean, that equation is pretty simple. Okay, I'll just have a look. So gallium reacting with oxygen, so that's the same as aluminium reacting with oxygen, and you can balance it. 2 of this, 3 of this, and 4 of this. Did you use the oxidation number of gallium over here? What's the oxidation number of this thing?
Positive 3.
Okay, that's +3. What is the equation or formula of the product that would happen when gallium oxide reacts with HCl?
So gallium chloride.
Okay, and what is the formula? Gallium is +3, right? So it's going to be GaCl3.
Cl3.
So what happens when you react it with hot concentrated NaOH? What is the equation for that?
So gallium hydroxide.
No, it's remember aluminum oxide with NaOH. If you react and if you write the equation for that, that's going to be sodium aluminate, which is NaAlO2, or you can also write it as NaAlOH4. TK plus water. That's going to be your product. So over here, it's going to be Na, Ga, and O2, right? TK or GaOH4. That's both of them are fine.
Sir,
Yes.
after this paper, could we do like the February, March one, like the newest one?
I have that. We'll do that. So what is the relative isotopic mass? So remember, relative is compared to carbon-12. So it's the mass of an atom of an isotope compared to 1/12 the mass of a carbon-12 isotope. I did send you the definitions, TKS. The next part is a sample of copper contains 2 isotopes, copper 63 and copper 65. The relative atomic mass is provided, and the sample of the mass is 63.5. Calculate the percentage abundance of each of these isotopes. So you don't know. Now you don't know which one is which percent. So you'll take this as X%. The other one would then be 100 minus X%, TK automatically. So if this is 30%, that would be 70%, and so on. You'll use the same formula, which is what is AR? AR is already calculated. It's 63.55. And So or AR is what percentage, which is the first one is X% over 100 into 63, plus the other one, which is 100 minus X% over 65. Be very careful with the calculations on your calculator when you're doing this. Sorry, this is not 100 actually. This, don't make silly mistakes like these. So 100 minus X over 100, right? And you take the 100 on the other side, it's going to become 6355 is equal to 63X plus 6500, I guess, minus 65X. You solve this further, what do you get? It's going to be 2X on one side or minus 2X on one side. And what is 6355 minus 6500? That's going to be 145.
Minus 145.
Okay, Baki, you just have to divide by 2 and you'll find your answer, which is
72.5.
सर
हाँ जी
सर ऊपर आपने क्वेश्चन किया था वही स्टेप्स वाला in which we had 2 stages. Sir, उसमें can we like describe in word equations like पूरा अगर हम reaction लिखते हैं word equation?
नहीं कहाँ पे किस वाले पार्ट में?
सर the ऊपर है.
एक सेकंड में आता हूँ. Just 1 second. ऊपर कहाँ पे ये वाला?
Yes sir, यही वाला. Calcium oxide.
नहीं, include relevant equations means include relevant equations. ठीक है? There's no, I mean, you have to write it. ठीक है? Just make sure. ठीक है? The number one thing is, I'll just give you a few tips. I mean, make sure whatever happens, just read the question instructions carefully. If they write the word state, that just means you state the answer. Like over here, I mean, if they ask you to write an equation, it has to be an equation. Okay? So read. If they want you to explain something, then you have to go into detail. Okay? When they use the word explain, you have to go into detail. So, like over here, they weren't really wanting the explanation part. They just wanted you to describe the two reactions and how would you convert something. So it was a direct question. Okay? Make sure that, like over here, state one common use, just state it. That's it. I mean, no further explanation. They don't want how does it neutralize the acidic soil. Okay? So make sure you understand what this means. And when you read the word explain, that means go into detail. Okay? Explain everything. As I'm moving on, we did solve this one. Name the type of bonding that occurs in solid copper. So what's the bonding in solid copper? That's that's obviously metallic. Metallic bonding, you have to describe what metallic bonding looks like. It's a bunch of metal lines in a sea of positive metal lines in a sea of free moving electrons. As one more tip, it's better not to do things with pencil. I mean, the pencil is allowed, but it's better not to do things with a pencil because when they scan papers, the pencil gives you very horrible results.
So what about the graphs?
Even that, I mean, the preferred choice is a pen, or at least if you're using a pencil, make it dark enough. Okay, make it really dark because remember your papers are going to be scanned, and if you're using a very light pencil or you're not writing clearly with a pencil, then scanning becomes an issue. And especially when you erase something with a pencil, that becomes a big issue. Like if you make a line and then you rub that off and then you make another line, both lines actually get scanned on the paper. So if you're using a pencil, make sure don't erase and rewrite on top of it. That creates problems while scanning. Okay, so remember the pen is the preference. Okay, it's and one that that is really clear, and not that inky. Like also make sure that your pen isn't producing a lot of ink, because sometimes what happens is that what you write behind the paper, that also becomes visible on the front of it. So just use a ballpoint. That's the best option. Achha, so copper, remember copper and chromium, they're two special cases. The original electronic configuration according to the off-power principle is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 9. But copper is a special case. Instead of having 4s2 as the stable electronic configuration, it actually has this electronic configuration as a stable one. It's 3d10, 4s1. And also remember, make sure you write the orbitals in the right order, not in the order in which you're filling it according to the off-power principle. I mean, when I was filling it, I did fill the 4s first and then the 3d. But the order has to be correct. The outermost should be on the outside. As the next one, you've got a moles question. A student provided with a sample of hydrated copper 2 sulfate. So this is about finding what X is. So this is about finding what X is, and is asked to determine the value of X. The student dissolves a sample of the hydrated copper 2 sulfate in water and adds it in excess of potassium iodide to make a total volume of 250 cm3. First thing, just sketch what's happening. There's a sample of this thing, and he's making it into a 250 cm3 solution. So you got a 250 cm3 solution, and that 250 cm3 solution is copper sulfate. But then what he does is he's adding potassium iodide to this thing. So this 250 cm3 solution, the copper sulfate reacts with the potassium iodide to form copper iodide, iodine, and K2SO4. So now what you have in this beaker is you've got a 250 cm3 solution that's got copper iodide, iodine, and K2SO4. Okay, so I just sketch everything. That's just a second. So what did he add in this? He added Ki. So Ki was added. Now 25 cm3 of the iodine containing solution requires. So now he's taking a 25 cm3 sample, a tiny sample of this original solution, and he's now reacting it with sodium thiosulfate. So he's now putting in sodium thiosulfate into it, and so the sodium thiosulfate is 20. Can anyone tell me what the moles of sodium thiosulfate are? What's 20 cm3 of 0.1 mole per dm cube? What's 20 into 0.1 divided by 1,000?
0.002.
02 or 002? It's
0.002.
okay. So he's adding thiosulfate from the top, and that's 0.002 moles. So we figured this out. We've figured out that the amount of thiosulfate that's being added is 0.002 moles. So what is the amount of iodine in the flask over here? That's going to be half of that. It's 2:1 according to the equation. So the moles of iodine over here would be 0.001 moles, right? And remember, the difficulty with this question is they didn't give any steps. Everything has to be done. I mean, a lot of moles questions are simpler because they give you a lot of steps. The problem with this question is they just gave this one big question. So I figured out the moles of iodine over here in this solution. I've got how much? I've got 0.001 moles of I2 according to the equation 2:1. So what is if that is the amount of iodine in 25 cm3, what is the amount of iodine in this 250 cm3 original solution? That's going to be 10 times more, right? So how much iodine would there be? That's going to be 10 times more. So over here, the amount of iodine would be 0.01 moles. Okay, is that clear?
Yes, sir.
Yes.
Okay, 25 में ये था तो 250 के अंदर it's going to be 10 times more. So you figured out the amount of iodine in the original reaction, which was happening over here in the copper sulfate. You figured out the reaction. So it's 0.01 moles. So the next thing is he's asking you to calculate the amount in moles of copper to sulfate. So the next thing is it's 1:2. So the amount of copper sulfate would be twice that. So it's going to be 0.02 moles, right? So that's the first part that is done. But make sure you present your answers properly. Like we've done the rough work and we've done sketches, TK, but when you're writing this, tell them what the steps are. I mean, tell them the whole detail, like the steps have marks. What was the first thing that we did? We calculated the moles of thiosulfate, S2O3. To minus, how did we do that? Write that as well. How did we do that? We multiplied the volume with the concentration. It was 20 divided by 1000 into 0.1, and that came out to be 0.002 moles. The next thing was we figured out the moles of iodine by using ratios, and that was, so we figured out the moles of iodine in what? In 25 cm cube. And it was 0.002 divided by 2. Okay, make sure you present your answers properly. After that, what we did was we figured out the moles of iodine in the 250 cm cube. So the moles of iodine were figured out in 250 cm cube, and that was 10 multiplied by 0.001, which came out to be 0.01 moles. And then we figured out the moles of copper sulfate from the first reaction where you had the moles of iodine. So the moles of copper sulfate were half of that. That was, or double of that. That's 0.01 times 2. Okay, so remember to follow this. I mean, don't answer too randomly. Even if your answer is correct, I mean, there's at least 1 mark, at least in this case, for the working as well. I say, anyways, we figured out. Now he's asking you to figure out the value of X. So how are you going to do that? That's there's a total of 7.98 grams of copper sulfate in 10.68 grams of this thing. So this is 7.98 grams. And so what is the mass of water in the sample? That's going to be 10.68 divided by 7.98. What value do you get?
Divided by or subtracted by?
Subtract, because I mean the whole thing is 10.68 grams, right? And
Yeah,
out
no,
of that,
I thought you said divide.
ठीक है. तो क्या आ रहा है इसका?
2.7.
ठीक है, 0.7?
2.7.
2.7, ठीक है. So this one is 2.7 grams. So now you have to figure out the moles. It's he's asking you to figure out the amount in moles. So it's going to be 7.98 divided by, I mean, the space is given for the working. Okay? Don't be too direct with your answers. Show the working. Because remember, you can go wrong on your calculator. So you might get full marks if you just made a silly mistake on your calculator. So make sure, tell them exactly what you're doing. So the examiners can be lenient on you. So it's going to be 7.98 grams divided by the MR of this thing. So it's 63.5, I guess, plus 32, 16 into 4. That's I say, and also remember, make sure don't use the values that you just remember. Sulfur is actually 32.1. Be as accurate as possible. So what do you get for this? 63.5 plus 32.1. Or uske baad you've got 4 oxens.
159.6.
Okay, and the next part is, I mean, what's the final answer?
0.05.
Exact?
Yes.
So you're going to write 0.0500. Remember, your values are accurate up till 3 significant figures. So your answer should be accurate up till 3 significant figures as well. This one is easy. The moles are, it's 2.7 grams. And that's going to be divided by 18. That's the Emma. What do you get for this?
You're 0.15.
0.15, right? So you're getting 0.15. And is there anything after that? I mean, I'm assuming there's nothing after that. So it's 0.150 to get 3 significant figures. Now, the next thing is you just have to figure out the value of X. So you just have to use ratios. It's You know that what is the ratio of copper sulfate to water? The ratio that you have figured out is that it's 0.05 of this and 0.15 of this. What's the whole number ratio? If I have 1, what would I have over here? That's going to be 3, right? So that
Yes.
means X is 3. So X comes out to be 3. The next part is we've got.
Sir, can you please explain the last part again? Why is X3?
No, because I mean, what is the formula? The formula tells you, like, whenever you have a hydrated salt, all hydrated salt questions end with in this way. That you're looking for, like, if I have 1 of this, how many water molecules will you have with it, right? So I just want to figure out the ratio that if I have 1 copper sulfate, so in the hydrated salt, how many water molecules will I have? So if I have 0.05 of this and 0.15 moles of this in the crystal, so according to the ratio, that's 1 ratio. Malika ratio, it's 0.05 ratio 15. That's or 5 ratio 15. So it's 1 ratio 3, right? So that means 1 copper sulfate has how many water molecules? It's got 3 water molecules next to it. Is that clear?
Yes, sir.
That's the next part. We've got suggest a name for the reaction that occurs when sucrose reacts with water to form glucose, and so it's a white crystalline solid, that's sucrose, reacts with water and aqueous hydrochloric acid. What is happening when a molecule of water gets added and the molecule breaks down into 2 pieces? What name is given to that reaction?
Hydrolysis.
Okay, that is no, that's hydrolysis. There's a difference between a hydrolysis and condensation. In condensation, you get one product. In condensation, what happens is that, like, esterification is condensation. In condensation, what happens is, if you've got a carboxylic acid and an alcohol, 2 molecules. I mean, the reverse of this is actually condensation. 2 molecules join up and they form an ester, and a water molecule gets produced. So in that case, so hydrolysis is kind of the reverse or the opposite of condensation. As if with this one, if no catalyst is added in reaction Z, the reaction is very slow. And what is the effect distribution to label the Boltzmann distribution to show the effect? I mean, it's already labeled adding a catalyst to the sample. So what will happen is you're going to add the only 2 labels that are missing are probably the activation energy one. So this is the activation energy, and let's say this is the activation energy with a catalyst. So you're going to describe, label the diagram, and what are they looking for to show the effect of adding a catalyst to the sample of sucrose. So why does the reaction speed up? So initially you had without catalyst, you'll have, or with a catalyst. I mean, what does a catalyst do? It lowers the activation energy. Okay, so the catalyst lowers activation energy. Now more particles or more molecules have energy that is greater than the minimum required energy, than the activation energy. So previously only these particles were energetic enough, but now it's a lot easier for the reaction to happen. So even these particles are now able to take part in the reaction. So they're energetic enough, they'll have vigorous collisions, or they'll collide and the reaction will be successful. So more molecules have energy greater than activation energy. So what you'll have is more frequent, and or the frequency of effective collisions increases. So the number of effective collisions, they increase.
सर इसके अंदर हम कर्व नहीं बनाएंगे, वो कैटलिस्ट के साथ कि हम वो जो रिएक्शन के बाद तो कर्व लोअर हो जाएगा और आगे शिफ्ट हो जाएगा.
नहीं, remember catalyst कुछ भी नहीं करता, ठीक है? Catalyst doesn't do anything. It just lowers the activation energy. What you're referring to is if you take it to a higher temperature. If you take it, the other question is, I mean, you'll get two types of questions. One is about catalyst, this one. The other one is what will happen if you take the reaction to a higher temperature. So if you take it to a higher temperature, the curve shifts to the right. So that one, let's assume in that one, you don't have a catalyst. So the activation energy is not lowering, but what will happen is if you increase the temperature, now you have more particles at higher energy. So again, the frequency of effective collisions would increase. You'll have more effective collisions because now you have a greater number of particles on the higher energy side. Okay? Is that clear?
Yes, sir. मैंने वो गलती से confuse कर दिया.
You can explain what is meant by the term chiral center. That's a carbon atom that is bonded to 4 different groups or atoms. On the diagram of the fructose molecule, label all the chiral centers within with a star. And is this chiral, this one?
No.
Okay, so, but the next one is, right?
Yes.
And this one is also chiral, and this one is also chiral. And that's it. You'll have a total of 3 chirals. Empirical formula, that's easy as well. That's 1, 2, 3, 4, 5, 6.
So what about the next carbon? Isn't it a chiral?
No, if you have a double bond, it's never going to be chiral. For chiral, you need 4
functional groups.
4 different functional groups and 4 single bonds.
All right.
Okay. Achha, so as the next one, you've got empirical. I mean, you can do empirical formula. Explain what is meant by the term enthalpy change of combustion. So it's the energy released when what happens when 1 mole of a substance or compound burns in excess oxygen. Okay? Remember to use the word excess because it's complete it's complete combustion, excess oxygen.
Can't we say completely reacts with oxygen?
Okay, but make sure better to use the word excess oxygen.
Okay.
Okay, measured under standard conditions. Although they didn't use the word standard, so that's probably going to be irrelevant over here, but measured under standard conditions. Write the equation for the complete combustion of sucrose. That's probably going to be easy as well. That's C12H22O11. So C12H22O11 plus O2 and CO2 plus H2O. 22, so that's 11 H2Os, 12 carbon dioxide, that's 24 plus 11, that's 35. And is this balanced or not?
No, sir.
Because that's 24 oxygens plus 11, that's 35, right? 24 oxygens plus 11, that's 35 as well. I think I mean you can check, you can double check, but I think it's balanced. I said now. I said this one, a lot of people have confusion with this. Use the data in the table to calculate the enthalpy change for the reaction. You should draw a labeled Hess cycle to show you're working. So if you had used the formula, that would have been very easy, but now they're looking for the whole Hess cycle. The formula was easy, like you just, if you have any reaction, and so what are they looking for? That's what are they specifically looking for? They're looking for the enthalpy change of reaction Z. What is reaction Z? 1 second. Delta HR can be calculated using, which is delta HR?
Sir, previous page when the sucrose becomes glucose and
this one. So I guess you would have to, that is reaction Z, right? So C12H22 water. So what is given to you? What they've given us is that it's the enthalpy of combustion of glucose, fructose, and so this one is, I'll make the cycle over here. But what's the formula? The formula is simple. Like if you have a formula and the enthalpy, if you have any reaction, remember the reaction could be any reaction. If the enthalpy of combustion of the reactant is given and the enthalpy of combustion of glucose and your products is given, what is the enthalpy of combustion of water over here?
Is it 0?
Okay, that's 0. Okay, remember carbon dioxide and water, the enthalpy of combustion is. So you by default know this. So if the enthalpy of combustion of the products and reactants is given, then it's just simply reactant minus products. But in this case, they're asking you to draw the whole Hess cycle as well. So what happens when you combust these things? It's going to produce carbon dioxide and water, right? And similarly, what happens if you burn this? It's also going to produce carbon dioxide and H2O. Is that clear? I mean, that's the Hess cycle. It's a simple Hess cycle. So how many carbon dioxides would be produced? I mean, it's going to be what? It's going to be 12 carbon dioxides, and there's going to be 11 plus 1, that's 12 H2Os. Again, you're probably going to get the same amount of carbon dioxide and water that's going to be produced. So it's the enthalpy of combustion, it's 1, 1. So the answer would be simple. The only arrow that needs to change direction is this one, that you're going to go from this point all the way to this point. So this arrow over here, its direction has to be changed. And everything is 1 mole. 1 mole of this reacts with 1 mole of this to produce 1 of this and 1 of this. So this arrow needs to be changed. So you're going to sketch this Hess cycle. Is this Hess cycle clear?
When you do the Hess cycle, can you just like write CO2 plus H2O, or do you need to balance it?
I mean, it's better to balance it. The problem will come with the oxygen balancing, because I did not include oxygen over here. There's no need to include the oxygen. TK, even in the market schemes, they don't include the oxygen, because obviously, where did the extra oxygens come in? You were obviously burning it with oxygen, so you didn't include that. You just turned the carbon and hydrogens into carbon dioxide and H2O. So at least make sure that's 12 CO2s and 12 H2Os that are getting produced, right? Is that clear? I mean, there's no need to include the oxygen on either side. That will make the balancing whole, I mean, almost impossible. Okay.
Sir, why did you change the direction of that arrow?
We had to figure out, I mean, we want to go from this path to this path, right? I mean, that's the path we're trying to figure out. What's the alternate path? The Hess law is that the enthalpy change of the reaction is the same no matter what path is taken. So that was one path. That's the alternate path. So you're going from this point to this point, and then from this point to this point. I mean, we want to make this thing, right? So this is your path. So this direction has to change. Is that clear?
Yes, sir.
Okay. Combustion was in this direction. This combustion was also in this direction. They were both producing carbon dioxide, but you want to go from this side to this side. Okay. So all that needs to happen is that these two, their enthalpy changes, they must be changed. I'll add in the values. Sucrose is minus 5643. So sucrose is this one, that's minus 56. That's minus 5643. And these two burning was what? It was minus 2805 and minus 2810. So this was minus 2810. So their values need to change. So it's going to be enthalpy of combustion of the reactants minus the enthalpy of combustion of the products. So it's going to be minus 5643. Their sign will change, and that's going to be minus 2805 and minus 2810. So basically what you're doing is you're doing the enthalpy of combustion of the reactants minus the enthalpy of combustion of the of the products. Okay, that's what you're doing. So that's your final answer. But without the Hess cycle, things would have been very simple. Just enthalpy of combustion of the reactants minus the enthalpy of combustion of the products. You're getting the same thing with the Hess cycle as well. TK, is this clear?
Yes, sir.
Yes, sir.
I said next one, there's a hexane. It's a colorless liquid, and 2 test tubes containing equal amounts of hexane, 1 cm³ bromine is added to both test tubes. 1 test tube is kept in the dark. Remember, he's talking about an alkane, which is hexane. When will the and the reaction is with bromine. What kind of reaction happens in sunlight?
Free radical substitution.
Yeah, that's going to be free radical substitution. Any of the hydrogens in the alkane will get substituted. So the bromine reacts. But obviously in the dark, it's not going to react. You need UV light for that. So explain the observations in the dark. The simple answer is that why is there a reaction happening? Because free radicals are being produced. UV light or sunlight produces free radicals of bromine. The bromine molecule, it breaks homolytically, and free radicals are produced, and that's why free radical substitution happens. You can't have a reaction in the dark. Why? Because there's not enough energy to break the bromine bond. So that's why the reaction is not happening. I mean, you should write that as well, because it's a 2-mark question.
Sir, can we say it doesn't have a double bond, so you can't carry it out in the dark?
He doesn't have a. He's never actually mentioned about. He hasn't said anything about anything being an alkene. So we should not bring that up.
Okay.
ठीक है कि मतलब जो चीज है ही नहीं वो क्यों आप बीच में डाल रहे हो? I mean, so that reasoning would not probably work. I mean, the other reasoning why it's not happening in the dark is that maybe it doesn't have enough activation energy or not enough energy in the dark. To produce the bromine radical, to homolytically break the bromine molecule and produce the Br radical. So next one is state the name of the mechanism. That's obviously free radical substitution, and give an equation which shows a propagation step in this reaction in which hexane. So I'll go through the whole free radical substitution. So I've got a hexane molecule. Now a hexane is a big molecule, so I can't really draw the whole of it. It's probably C6H14. What happens is, just after this. So what happens is that these are all hydrogen atoms, right? So this is free radical substitution, that in the first step, in the very first step, bromine radicals are produced. I'm just going to do the whole working over here on this page. The bond breaks homolytically. Why does it break? Because there's UV light coming in, and that's providing the energy to break the bromine bond. A bromine radical is basically just a bromine atom. A radical is anything that has incomplete bonds. So even if carbon has incomplete bonds, that's a radical. They will try to complete their outer shell. They have odd number of electrons. So when a bromine radical is formed, what it will do is that bromine radical would attack this hexane molecule. So, and it can steal any of the hydrogen atoms. So any of the hydrogen atoms, they can be, because bromine needs to complete its bond. So it comes around and steals the hydrogen. So what happens is that a bromine radical attacks a hexane molecule and steals one of the hydrogen from the hexane and ends up forming HBr. So these two end up forming HBr. Now one of the carbon and that HBr, let's say it leaves. So one of the carbon now has a missing bond. It's making only 3 bonds. So that's now a radical now. So the hexane C6, now it's H13. Now it's a radical. One of the carbon is a radical. So that's the first step. Now what that radical does is it tries to complete its bonds somehow. So what it will do is, if it sees a bromine molecule, what it will do is it will try to steal that bromine molecule's bromine and try to join it with it. It's going to try and bond with it. So the next step is that C6H13 radical will attack a bromine molecule whose bonds were complete, but it will steal one of the bromines. So now it's going to become C6H13, and there's going to be one Br that's going to be added to it, and another Br radical would be produced. When this Br leaves, its bonds are now incomplete. So now this bromine has joined this carbon atom, and now you've got another bromine radical that's roaming around. That bromine radical would attack one of the hydrogens and take away. So the same propagation step would repeat over and over again. So give an equation which shows the propagation step in the reaction which hexane produces C6H13. So what happened was C6H14, a bromine radical came in, took away one of the hydrogens, formed HBr, and left a hexane radical. It would be called a hexyl radical. Now give an equation which shows a propagation step in this reaction that produces one bromohexane. So he's probably talking about this one bromohexane. So once this radical, and I forgot to put the dot. So once this radical is produced, you get this one over here. This one will attack, it will try to complete its bonds. It's going to attack a bromine molecule, take away one of the bromines, and another bromine radical would be produced. Same thing, same step repeats. This bromine radical would attack one of the hydrogens, take it away, form HBr. The radical would reform. So give an equation which shows a termination step. What's a termination step? A termination step is, once these two are fighting over atoms, the bromine radical is stealing electrons from the carbon or any of the hydrogens, while at the same time, the carbon radical is stealing bromine atoms from the bromine molecule. The termination step is any two radicals could just get together and that would be it. So for example, you have a C6H13 radical. Why is it a radical? Because one of the carbon is missing a bond. In the first step, right in the first step, you had bromine radicals. Why was that a radical? Because bromine was missing a bond as well. So why don't they just bond with each other? That would form C6H13 and Br. And that results in the production of no new free radicals. The free radicals, they get used up. That's the termination step. Once the radicals are gone, the reaction would stop. So give an equation which shows a termination step in this reaction that produces one bromo. So this is that reaction for number 4. So is this clear?
Yes.
Yes, sir.
As a next is you've got just a second. Let me. As the next is we've got just hold on 1 second. As A and B are different straight chain alkenes with molecular formula C6H12.
Sir.
Haji.
Sir, do we have to draw the electron with the radicals?
You will a dot to it?
Ji, sir.
I think it's better to actually draw that, because
okay.
That would clearly because you never know, are they looking for it or are they not looking for it. Make sure to always not answer things partially. Make sure try to answer things as fully as you can. So okay. Drawing the dot, even if it's not written in the mark scheme, draw the dot. Because sometimes, because a lot of things, remember when the examiners are checking, there's a lot of subjective checking as well, because the examiner would have his own ideas. So it's better to, if there's some examiner who thinks that there should be a dot on top of that, he might cut 1 mark. That's why you get different marks when you get your papers rechecked. So it's better to answer as fully as you can.
So you'd write the curly arrows too then, right?
In this case, that would not be possible actually, because remember, first thing, you can't draw this whole thing in this one line. So I guess, I mean, if you had, I mean, there's not room enough for drawing the curly arrows. I mean, for the first one, you might.
There was a question on paper where you had to draw the curly arrow. There was a mark.
But I'm saying about this one. I mean, if you had a choice, you should draw the curly arrows as well. But the problem over here is that you got a very big molecule and there's not enough space. So I don't think there's any way you can fit in the curly arrows over here. So I guess that's out of the question in this case. If you had space, then we should have gone with the curly arrows. Okay. But probably not in this case. You don't have enough space to draw the curly arrows. As the next one, you've got A and B are different straight chain alkenes with molecular formula C6H12. A does not show stereoisomerism. A reacts with potassium magnate 7 to form hexane 1,2 diol. So starting with this one, hexane 1,2 diol. We can do everything in reverse. So when do diols form? So when do diols form? That's mild oxidation, right? So you've got hexane 1,2 diol. So that's 3,3, 1,2 diol. That's OH over here, and that's there's an OH over here as well. Where would the position of the double bond be in A? I mean, that must be over here, right?
Yes,
that's
sir.
Why, that's why it's forming a diol. So it must be over here. So that's your structural formula. Okay, and all you have to do is remember they're asking for the structural formula. So when they ask for the structural formula, that's the most general version of the formula, which is that you can draw any formula that shows structure. So if you have room, draw the displayed formula. That's I mean, you can even draw the condensed one. And in this case, even skeletal would be acceptable. So this one, that would be sufficient. State the conditions needed for this reaction of A. So what are the conditions when you want to form a diol? Okay, what are the conditions for diols?
Acidified KMNO4 and heat.
Oh.
No, but is it? Just remember that you've got two types of oxidations. You've got a mild oxidation, which is cold dilute alkaline cold dilute acidified KMNO4. And you've got strong oxidation, which is hot concentrated acidified KMNO4. So in this case, it's going to be cold and dilute, and obviously acidified. Now the next one, B reacts with hydrogen gas in the presence of platinum catalyst to produce hexane. Name the type of reaction. What type of reaction is this? Like an
oxidation.
You've got an alkene.
Addition.
But what is alkenes? Remember, alkenes have an addition reaction. You can describe this reaction in two ways. You've got hexane is big, so I'm going to draw a smaller molecule. Let's say I'm drawing ethene, right? Hydrogenation is all alkenes reactions are electrophilic addition or simply addition. So the H atoms will get added. So this is, and the double bond would go away. So that's addition. The other name for this reaction that can be used is reduction. Whenever you have hydrogen atoms getting added, that's reduction. Hydrogenation is not the type of reaction. It's name given to a reaction, and it is correct. But when you refer to type, you've got three types. You either have addition, you have substitution, and you have elimination. Or you can include reduction You can include redox or reduction and oxidation in this as well. So alkenes always undergo addition. Alkanes always undergo, most of the time it's substitution, like free radical substitution. Halogenoalkanes, that's free radical substitution. Aldehyde and ketones, they have nucleophilic addition. The double bond O reacts. Now, in terms of sigma and pi bonds, describe any similarity and difference in the type of carbon-carbon bonds in B and the type of carbon-carbon bonds in hexane. So what is the difference between the carbon-carbon bonds in an alkene and in a hexane molecule?
So alkene has a double bond, one sigma and one pi bond.
Okay, so B has a double bond, and you're going to describe that it has what is a double bond? Whenever you have a double bond, that's one sigma and one sideways overlap, which is pi bonds. While what will happen in that hexane? That's only sigma, right? So that's the main difference. There's one pi bond in this alkene.
Sir, speaking of pi bonds, I remember like there was a thing where electrophiles will attack the pi bond specifically. Could you explain that, please?
I mean, that's this one. That's electrophilic addition. That's all electrophilic addition reactions. You see, you've got an alkene, right?
Yep.
So the pi bond is you've got an electron-rich center. You've got sideways overlap of orbitals. So there's a lot of electrons over here. Yeah, so the positive bromine is basically attracted to the pi electron cloud over here. Is that clear?
All right. All right, sir.
Okay.
Thank you.
So I mean, this is the positive bromine, or the electrophile is attacking the pi electron cloud. So the first bond that goes missing is the pi electron cloud over here. Who took it? The bromine took it.
All right. All right. Thank you, sir.
As the next one, so let me just check the questions that were sent.
Sir, can we also do a couple of questions of mass spectral?
ठीक है, वो कर लेते हैं. Just a second. So let me just open these questions just 1 second. So this one, the first one. I have these questions. A student was asked to reduce the full structure of L. So I guess you don't know what R is.
What paper is this? Or
no, we're not sure what paper this is.
All right.
So there's this question, and they've given us what L looks like, right? This one second. They've given us what L looks like, and we don't know what R is, and they've told us the infrared spectroscopy. First thing, I mean, this part is easy. You just have to figure out what X and Z are. So Z is, you can go and open the data booklet. Z is C single bond O. At 1000, if you look at the data booklet, that's single bond O, and at 1600, that's C double bond O. I mean, you should memorize that. I mean, these two are the easy ones to spot. Like if I open the data booklet, just 1 second. Remember that you get a lot of questions about. Just 1 second. Where's the? So this is your infrared spectroscopy. 1000, that's C single bond O, C double bond O, that's 1600, 1700, somewhere in that range. So you would be easily able to identify this one. X over here is definitely C double bond O. So we're done with that. The next part of the question is that absorption Y shows that L has a C, double bond C present in the R group. So not really sure what Y is. Y is, they've given us a Y as well. So they're saying that it has a C double bond C as well. The student decided to treat L with hot concentrated acidified potassium magnate. Just a second. So they decided to treat it with hot acidified potassium magnate 7. The products of this reaction are shown. Name M. So they're using hot concentrated KMnO4. And let's do this one just a second. And let me, is there any way to increase the size? So I'll just do this over here. Just 1 second. I just hope it doesn't have. I said this one. So I said this one. So I've got this and this. These are the products. And they've told me the problem is with this R thing, right? And when you do hot concentrated KMnO4, what happens? You got 3 options. You got double bond, and the double bond would completely break. So what are the 3 options? One is that if you have H atoms on both sides, if you've got H atoms on both sides, what will that produce? What will that carbon atom produce if you have got 2 H atoms?
Carbon dioxide and water.
Inside in water.
Okay, carbon dioxide and water. And if you have got 1 carbon chain and you've got 1 H, right? So what will that produce?
Carboxylic acid.
Carboxylic acid. So basically, this carbon over here is producing a carboxylic acid. So it must be a carbon making a double bond, and it will have 1 carbon chain. And this carbon over here is also producing a carboxylic acid. So that means the double bond, which is not shown, is probably going to look like this. So I'm going to draw this. I'm going to connect these 2 carbon atoms. They would be connected together with a double bond. So let's do this. Like the first part is how many? 1, 2. There's an O, and there's this, and there's a double bond O. And I've got this and this. So let's focus on this carbon atom. It's making a double bond, right? So it would have 1 H and 1 carbon chain. Is that clear? So it must look like this. Like when the double bond was breaking, this carbon had 1 H, and on one side it had a carbon chain. Is that clear? Okay, and this other one.
Yes, sir.
So and this other one. This other one is also going to be the same. It would be a carbon that would be making a double bond. It will have an H, and on one side it will have a carbon chain. So this carbon has a carbon chain. It's got 4 CH2s. So it's got 4 CH2s. And 4 of them, right? And then at the end, it's got a CH3. So this is the original molecule, that this R is basically this thing. That you had a molecule, you did hot concentrated KMnO4 oxidation, and you ended up with 2 products. And when you figure out the products, you figure out that this one has a carboxylic acid, this one also has a carboxylic acid. So when does an alkene form a carboxylic acid? That it was a double bond. And before breaking the double bond had 1 carbon chain and 1 H. Now, so I figured out that this must be a double bond, and it will have 1 H only. On one side, it will have a carbon chain. I figured this one out as well. This one would have been a double bond with 1 H, and on the other side, it would have a carbon chain. So I did that, and the 2 would be connected together. So once they break at the middle, this one will turn into a carboxylic acid, and this one will also turn into a carboxylic acid. Is that clear?
Yep.
Yes, sir.
And these ones are difficult. So doesn't the ketone one oxidize further? Just a second. Which one is the ketone one? There's no ketone.
Generally though, right? Ketones don't oxidize?
They don't oxidize. I mean, you got, sorry. Just hold on a second. So, I mean, let me explain over here. Yeah, I would have to delete this just a second.
If you download the image, you can write on it. Like
I think I'll try and do that. Just a second. How do I clear this? Just a second. So these questions are difficult. Okay, so I'll just practice a few more. We'll practice a few more questions. And hold on 1 second. And let me download all of these. The WhatsApp is getting stuck. Just 1 second. You just hold on 1 second. It's forming a zip file. So let me just do some questions related to this oxidation of alkenes. But let me do the questions first. We'll try and do the same over here with the next one. So again, it's the next one is kind of the same. Let me just show you. So now the next one, and let me annotate this. So it would have been a lot better if you just told me the paper number. But this one, similar question. You've got 2-methyl-butanene and it's producing C products. Okay, so this is, I think this is the one that we had, which I remember doing this one. So butanene, what's butanene? That's a double bond and 2-methyl. So you got CH2 and you got H's, right? So the double bond is going to completely break. What will this carbon turn into if you do strong oxygen? Sorry, just a second. So can you see this question now?
Yes.
Yes.
So what will this turn into? This will turn into the first carbon atom over here. The double bond would break. Okay, what if you have 2 carbon chains? That's going to turn into a ketone, right? And it's going to be this one, the one that's drawn over here. It's going to turn into a ketone. The C would turn into double bond O, and you'll have a CH3, and the other one will be CH2, CH3. Okay. And what will happen to this one, the carbon with 2 H's? What will happen to that? Okay, that's going to be CO2 and H2O. But before we did one question similar to this, before turning into CO2 and H2O, what will happen to it is it will turn into before turning into, it's going to turn into methanoic acid. Then it will turn into carbon dioxide and H2O. So over here, what the question is saying is that it's going to turn into methanoic acid, then it's going to turn into carbon dioxide and water. Is that clear? Just remember that. This is a recent question. So even before turning into carbon dioxide and H2O, it turns into, this side turns into methanoic acid. Okay, make sure you remember that. Is this clear?
Sir, can you please repeat it?
Okay, you had a double bond and the double bond would break. So you've got a carbon over here that has 2 carbon chains. So that, what will that turn into? That will turn into a ketone, right? Okay, this one, this carbon, I mean,
Yes,
this.
sir.
And over here, you've got carbon with 2 hydrogens. What will that turn into? That will turn into carbon dioxide and H2O. Okay, if you've got 2 hydrogens. You be clear?
Yes, sir.
The only point I made was that before turning into carbon dioxide and H2O, it's going to turn into methanoic acid first. It will first turn into methoic acid, then it will turn into carbon dioxide and H2O. Up clear?
Yes, sir.
So next one, just 1 second, इनको कर ले. So the next one is this one. As I keep getting this question, this is a relatively simple question. The only difference is that if you look at this question, you've got they're saying that they're using AS2S3 and 0.18 grams of this. So what you can do is you can find the moles. How many moles is that? 0.18, 0.198 grams. Okay, so we're going to find the moles of AS2S3 and divide by the MR. What is the MR of this thing? Can somebody try and solve this? What is the MR of AS2S3? I think it's 216.1. So what value do we get for this? What is the value we are getting for this?
(9.16 in 10 power minus 4.
9.16 into 10 power minus 4, right?
Yes.
I said now based on that, you can figure out the moles of he's reacting it with 0.1 dm cube of pure oxygen and excess. Now based on this, you can figure out the amount of oxygen that is getting used up, use ratios. So 9.16 divided by 2 into 9, what do you get for that? Like how much oxygen gets used up? What is 9.16 minus 4 and divided by 2 into 9?
4.12 times 10 to the power minus 3.
So you're getting 10 power minus 3. I said, now remember, this is the moles of O2 that has actually got used up. It's the one that's reacting, right? I said, what is the amount of, now remember, he's only interested in the volume of gas present at the end of the experiment. So what is the amount of SO2 that is produced using the same ratio? It's 9.16 divided by 2 into 6. What do you get for this? How much SO2 is produced? Like how many moles?
2.75 times 10 to the power minus 3.
Minus 3 moles, right? So that's the amount that is getting produced. So what's the final volume? I'm going to try and calculate the volume of SO2 that is produced first. Okay, that's the amount of gas that's being produced. That's how do you figure out volume? They've already told you that it's just a second. Just a second. Let me. This one. So I've already figured out the volume of SO2. You just have to multiply it by 24 dm cube. That's going to be 2.75 into 10 to the power minus 3 into 24 dm cube. So what do we get for this? You get the volume of SO2 that is produced.
Zero point zero 0.066.
0.066, right?
Yes, sir.
As a dm cube. I'll focus on the significant figures later, but that's what you're getting. I said that's the volume of SO2 produced. But remember, he's only asking about the calculate the volume of gas present. Okay? So SO2 is one of the gas that is present. What is the other gas that's present? Now AS24, this one is a solid, it's the leftover oxygen. Okay? So you have to figure out you have to figure out what is the leftover oxygen that is present. Okay, so leftover oxygen. Remember, you started off with 0.1 dm cube of oxygen. They gave you that initially you had 0.1 dm cube of oxygen, but how much reacted? Calculate the volume of oxygen that reacted. That's multiply this by 24 dm cube. So how much oxygen is taking part in the reaction? Nidana, which one are we going to multiply by 6? We already did that. So how much?
1.12 into 10 power minus 3.
1 point?
I've subtracted it from 0.1 already.
Ajay, you already did that. So basically what you have to do is this was second of so let me just 1 second. That's the ratio. Remember, we figured out the moles of this thing. That's 9.16 times 10 power minus 4. It's 2:6. So I did 2:6. When I tried to find the moles of SO2, it was 9.16 divided by 2 into 6. So we used that ratio already. And we found the moles of SO2. Once we found the moles of SO2, I was able to find the volume of SO2 that was being produced by multiplying by 24 dm cube. And I found the volume of SO2. But at the same time, they weren't looking for the volume of SO2. They were also looking for the leftover oxygen as well. So 2:9. So I figured out 9.16 divided by 2 into 9. That would give me 4.12 into 10 to the minus 3 moles. I multiplied that by 24 dm cube. I found out the volume of oxygen that actually reacted. So out of 0.1 dm cube, how much is reacting? What was the volume over here?
0.099. It's rounded off.
As a 99 dm cube. So that's the volume that reacted. So you're going to subtract that from 0.1 because 0.1 dm cube was the original volume of oxygen, and out of that 0.099 dm cube was gone. It reacted. So you are at the end of the day. So you're at the end of the day left with. What were you left with?
1.12 into 10 power minus 3.
So you're going to sum up this volume with this volume. That's the total volume of gas that is present. It's the gas that is produced. Okay. It's the gas that is produced, and it's the other one as well. As I said, I can't really solve this because my laptop keeps getting. I mean, I'll try and send the answers to these questions later. Okay. It's getting stuck. If you can just tell me what the paper numbers are, that would be a lot easier. It's still. I mean, my laptop is hanging up with WhatsApp.
Sir, can we do like mass spectroscopy questions?
Just a second. Let me clear this. Then I'll send a separate video on the other questions. It's very hard to open these questions right now. I'll just message you directly. Just 1 second. Let me clear all this. As a mass spectroscopy, remember mass spectroscopy. There's not much to it except for I'll do all the questions on mass spectroscopy. Let me open an A2 worksheet. Remember, things are going to be mass spectroscopy questions are going to be extremely easy. This one. As remember, mass spectroscopy questions are going to be extremely easy. You just have to remember 3 or 4 things. That's it. So first thing, when you do mass spectroscopy, you can figure out the number of carbon atoms. That's the first thing. So you should remember the formula of mass spectroscopy, which is, I mean, this whole question, that's an A2 question, but The very first thing is, if you know the M+1 ratio, you can figure out the number of carbon atoms. What's the formula? That's 100 over 1.1 into the M+1 height divided by the M height. So it's going to be 100 over 1.1 into 0.9 divided by 20.4. Okay, so what do you get? How many carbons do you get for this?
I'm getting 4.
Okay, so and it's going to be a rounded number. Okay, make sure you round it off. So it's going to be 4 carbon atoms. So that's the first thing with this formula. Just remember this formula. A lot of questions will have the rest is all A2 again, M+1 ratio. Just apply this formula. That's it. Okay, that's the first thing. It's a very basic thing. That's just the first thing. So ignore all of this. Again, M+1 ratio. Figure out the number of carbon atoms. Is that clear? That's the first thing.
Yes, sir.
The other thing is, I said the other thing is the molecular end peak. What you can also guess, if I go back to the question, what you can also guess from the M peak, the location of the M peak. The M is the mass of the molecular end, that's 74. So that's basically the MR, right? So you have a molecule that has a mass of 74. It's a relative mass of 74. And they've told you that it's a saturated alcohol. So what you can also guess is you can also figure out, like, it's 4 carbon atoms, right? So by looking at the M peak or the molecular end peak, that's the mass or MR of the molecule. So you got a 4 carbon atom alcohol. So you can figure out what kind of alcohol would it be? It would be, it's got 4 carbon atoms, so it's probably going to be C4. And or you can draw it. So it's probably going to have 4 carbon atoms and it's got an OH. And you can just check whether this is 74 or not. Okay, I'm not saying it's this one, but at least the molecular formula would be the same. Because the position of the OH could be, it could be anywhere. We don't know what the position of the OH is. But that's another thing that you can figure out. You can figure out the number of, the total number of atoms in a molecule. Or you can at least make a guess. Is that clear?
It's correct. Yeah.
Okay, that comes out to be 74. The only issue is mass spectroscopy only deals with mass. So it won't tell you where the OH is. So you're not sure the OH is at that position or the carbons are all in a straight line. So that's, you can figure out the molecular formula, but you can't really tell what the structure is. I said that's another thing that you can figure out. What else can you figure out? You can figure out the number of chlorines and bromines. That you can figure out by, the only thing you have to remember about that is that if you've got an M+2 ratio, now this one involves the M+2 peak. Why do you have a peak which has the mass slightly, greater by 2? Because chlorine has an isotope. It's got 35 and it's got 37. So if you have 1 chlorine, the mass of the molecule can increase by 2 as well. So in the case of chlorine, the ratio of the 2 heights would be 3:1. Because chlorine 35 will give you this mass and chlorine 37 will give you a mass that would be greater by 2. And the ratio or the abundance of chlorine 35 is a lot greater, so you'll get a lot more of this. It's going to be 3:1. So if you see this, that's going to be 1 chlorine. And if you've got an M+2 ratio and the ratio is 1:1, that indicates that you've got 1 bromine in the molecule. And you should remember the isotopes and their percentage abundance as well. Chlorine has 2 isotopes. One is 35. The other one is 37. So the 35 one has a percentage abundance of or probability of 3/4. The chances of getting chlorine 37, that's 1/4. In the case of bromine, you've got 2 isotopes. One is 79, the other one is 81, and both of them have equal probability. So maybe in the question, somewhere you might be given the M+2 peak as well, like over here. You might be given an M+2 peak. What ratio do you have over here? What ratio is this?
3:1.
Okay, that's 3:1, and that would indicate that it's got 1 chlorine. Okay, is that clear? And so which element is indicated? That's about it. Okay, you're not going to be asked much about it. Similarly, you might get a question on 1 second. You might get a question on bromine as well. So over here, he's saying that the M+2 peak had similar heights. So if they have similar heights, that means you got one bromine. TK, is that clear?
Yes, sir.
And the very last thing is about fragments, TK. The fragments will give you some information about, the molecule could break down into smaller pieces. So the fragments could give you some information about the structure. Like, for example, if you figure out that the molecular ion is C3H6, now you don't know which C3H6 is this, the left one or the right one. So you can do some guesswork by looking at the fragmentation pattern. What piece will be detected, or what smaller piece of the molecule will be detected over here and not in the other one? Like one difference in the fragmentation pattern. Smaller fragments would be obtained like CH3. If you obtain a CH3 fragment, you'll detect a particle which has a mass of 15. If you do fragmentation of this and you try to detect smaller particles, you'll never get a particle that has a mass of 15, because no smaller piece of the bigger molecule has a mass of 15. It's either 14 or it can never be 15. Is that clear?
Yes, sir.
Yes, sir.
So that's another thing that you would, the fragmentation can give you an idea about the structure. So if you're doing a mass spectroscopy of a big molecule, you'll obviously get the molecular ion peaks, like you're doing it for carboxylic acid. But you'll get all sorts of smaller particles as well. Like you might get an OH particle. So you might get something detected at 17. You might get a COOH particle. So that would be a mass getting detected at 45. You might get a CH3. That would be 15. So you can, by looking at the particle, you can do some guesswork. That this entire thing would be 60, right? It has a mass of 60. So that's the big molecular ion. That's your M peak. But if you analyze the small fragments, you can sort of like solving a puzzle. You can make some guesswork about the overall structure. Like if you detect some particle at 16, what do you think that is? I mean, what particle is 16 over here? It's probably going to be an oxygen atom, right?
Yes.
That an oxygen fragment. If you detect a particle at, let's say, 28. So what could 28 be? It might be CO, right? So,
yeah.
So you can get some tiny bits of information about the fragments that are obtained. Okay, is that clear? That's about it. The M+1 ratio tells you the number of carbon atoms. The M+2 ratio tells you the number of, if it's got 1 chlorine or 1 bromine. And then you have these fragmentation patterns. Okay, you can look at the fragments and you can make some guesses about the molecule. Okay, is this clear?
Yes, sir.
Yes, sir. On the screen, the B part, can you explain the second part of it?
No, that's not in your course. I mean, this is an A2 worksheet, okay? That's not in your course. I mean, all of these questions, they're not in your course, okay? It's just this very tiny initial part that's in your course. M+1, you figure out the number of carbon atoms. M+2, you figure out the number of CLs, that's it. I mean, the rest of the question is not in your course. Okay, is that clear?
Yes, sir.
So, but see, any other okay, I'm going to go back to the paper now. So coming back to the paper, we won question number 5, I guess. Did we do the? I said we had done that. I said let's start with question number 5. I'm going to do the February March 2022 as well after this. So I said so we've got CD and E are isomers of each other. They are made by passing an alcohol vapor over an aluminium oxide catalyst. So alcohol with aluminium oxide, what reaction is this? This is going to form an alkene. it's this one. You got an alcohol, it's dehydration. If you heat it with Al2O3 plus heat, it's going to form an alkene. Al2O3 plus heat is also used somewhere else as well, and that is used for cracking. Al2O3 and heat is also used for cracking. It's also used for forming alkenes. So, but it's also used for dehydration as well. So name the type of reaction that's first thing. What's the type of reaction that's happening in this case?
Dehydration.
Yeah, that's obviously dehydration. It's forming an alkene. Draw the displayed formula of the alcohol used in this reaction. So these are the alkenes that are formed. What would be the position of the OH group if these are the alkenes that are being formed? It's obviously going to have 4 carbon atoms, right? But where do you think is the OH group before it got dehydrated? First one, second one, third one, or fourth one? It's going to be on the second one. That's where the OH group, and you have to draw the displayed formula. So when you see the word displayed, draw the whole thing. Every bond has to be shown. So you got CH3H and so every single bond has to be, it's got to be shown. How did we figure out the OH is on the second one? Because the double bond would either be, the OH would be lost and the double bond would either be formed on the right side or on the left side. So why are we getting 3 isomers, 3 molecules? Why not 2? Like you're either going to have a double bond on this side or you're going to have a double bond on this side, right? So why did they draw 3 alkenes? I mean, one of them is a geometric isomer, like C and D are basically the same thing. The double bond has the same position. It's in the middle. But one of them is cis, and this one is cis. And this one is trans. Name the isomers C, D, and E. So what is the name of this one, E? The E क्या चीज़ है? The bute, that's 1, 2, 3, 4, that's butanene. And this one is butene. But the complete name would be, one of them is transbutene, the other one is cis-butene. Okay, so it's butene. As for next one, you've got this reaction. F is an organic molecule which has the molecular formula C3H6O2. F is heated with NOH followed by H2SO4. The products are G and H. So it's breaking down, probably alkaline hydrolysis. Separate samples of G and H are added to Na2CO3, sodium metal, alkaline aqueous iodine. So first thing, sodium carbonate, you're getting bubbles of gas. So who reacts with sodium carbonate? Like what group would react?
Carboxylic acid.
So G is a carboxylic acid. That's the one that's going to react with. H is not. So that's confirmed. Na reacts, and in both cases, it's forming bubbles of gas. So since it's a carboxylic acid, so obviously it's going to react with the metal as well. So what is H then? It is also forming. Okay, that's an alcohol, right? Because only 2 things react with. Only 2 things react with alcohols. React with sodium, and the other one is carboxylic acids. They also react with sodium, but they also react with NaOH, Na2CO3, and weak bases as well. So this one can't be a carboxylic acid, so it must be an alcohol. Alkaline aqueous iodine, you're getting a yellow precipitate. So who gives a yellow precipitate in the iodoform test? It's either going to be CH3 with a C double bond O, and you got a carbon chain, or you're going to have CH3. We already figured out it's an alcohol. So it probably is going to be an alcohol similar to this. It's going to have this structure. So the functional group that is present, first thing, This is an alcohol, this is a carboxylic acid. So what is F? What thing breaks down into a carboxylic acid and an alcohol?
Ester.
It's an ester, especially when you heat it with a dilute alkali or a dilute acid. So name the yellow precipitate formed. What is the yellow precipitate? The CH3 breaks down and it forms CHI3. That's tri-iodo. I mean, correct the spelling. That's.
Sir, can we write iodoform? I saw that somewhere in the marking scheme. Iodoform or something like that.
But the name is triiodomethane. The name of the test is iodoform. Maybe they call this iodoform, but the technical name is triiodomethane. Okay. So what's the next one? You've got draw the structures of G and H. So I'm pretty sure it's wrong. Iodoform is going to be wrong. Maybe in some market scheme they gave it, but they were probably. I mean, the name of the test is the iodoform test, but I guess it's when you have to name the molecule. This is triiodomethane. So pretty sure that iodoform would be wrong. I mean, if they were talking about the test is iska dekh lete hain, just 1 second. If you just to be sure, we can just confirm this. This one is S20 MS23. Just a second. Because they were specifically calling to name the
Sir, it was in 2018, summer 22. It was mentioned that in the marking scheme somewhere.
So maybe it got accepted, but over here it's triiodomethane. This is the more later. This is the latest one.
Okay.
Okay. So coming back to this, I mean over here they just gave you triiodomethane. That's it. That's the next one. You've got draw the structures of G and H. You already figured out this one is a carboxylic acid. This is an alcohol. But the alcohol is going to be the one which gives a positive test with triiodomethane. Now this thing has only 3 carbon atoms. So if this were to give an iodoform test positive result, it's got to be an alcohol with 2 carbon atoms. Because it's got to have this structure, CH3 with CHOH. So that's your alcohol. So you're left with, I mean, the ester only has 1 other carbon atom. So the carboxylic acid is probably going to be methanoic acid. So 1 carbon atom over here and 2 carbon atoms over here. Because I can't give a positive iodomethane, triiodomethane. I mean, it has to form triiodomethane. So there must be 2 carbon atoms in this molecule. Hanji.
Sir, could you go? Yeah, okay. So the F2G, right? It's what reaction is this?
This is hydrolysis. It's the ester breaking down into alcohol and carboxylic acid.
Yeah, okay, but they've they've used a base and an acid. So
see, listen, what happens is when you use alkaline hydrolysis, right? What happens is that the carboxylic acid ends up forming a salt instead of the carboxylic acid, right?
Yeah.
But if you don't want to, because you're adding too much alkali, right? So the alkali will end up reacting with the carboxylic acid. So to prevent that, you follow it by H2SO4. Like if you acidify it later, so that means the excess NOH got neutralized. Is that point clear?
Yeah, I get it now.
So it's going to form carboxylic acid in that case.
All right, perfect.
So here we're done with this. Which other paper do you want to do? The one.
So we do February, March.
Just a second. Let me check.
I have the paper if you don't have
I think it's this one. This is February, March, right? This is the latest one.
Yeah, sir.
So starting with the first one, construct an equation of first ionization energy of oxygen. So as a photochemicals, I'll just do photochemical smog very quickly. See, when you have a CFC, not really sure if it's going to come. It's I would have to check the syllabus, but the Cl radical homolytic fission happens and Cl radicals are produced. What happens is the Cl radical goes and attacks ozone. It ends up forming ClO, and O2 molecules are produced, and then those ClO radicals, they attack ozone again, and they form Cl radical and two O2 molecules. So that's how the ozone breaks down. So that's how Cl radicals in the upper atmosphere, when CFCs go into the upper atmosphere, Cl radicals are produced. But pretty sure that's I mean, I'll just confirm that. I'll check the syllabus. That mechanism is probably not going to be included. The only thing I guess you need to know is that the Cl or the CFCs will destroy the ozone. I think this one, construct an equation. So I'll just confirm the new syllabus. I'll just confirm this, TK.
Sir, what mechanism was that just now?
No, that's no specific mechanism. It's just the destruction of ozone that happens. When you have a CFC that goes into the upper atmosphere, the CFC breaks down due to UV light. It breaks down and the Cl radicals are produced. And those Cl radicals, they start attacking ozone. And the Cl bonds with one of the...
What about the photochemical smog thing? What was that?
Just a second. This is the... to form and it can form unburned hydrocarbons, can form nitrate, which is a component of photochemical smog, and decide the role of that's this one is added. Can react with unburned hydrocarbons. This one is probably, I guess, you don't have to go into details about this. I mean, obviously, you can't remember. I mean, this formula is too complicated for you. I mean, they just want you to know for this one that in cities, what happens is that NO2 and NO are produced because of car engines. So there's a lot of NO2 that's around. And because of the car engines, there's a lot of unburnt hydrocarbons. So the hydrocarbons and the nitrogen oxides, they react together, and that's this thing. And that is basically photochemical smog, which causes a lot of breathing problems. So I think you don't need to know the reactions for this.
They asked for the name.
Yes, sir, because I read the question and they were only looking for the name. PAN.
Because they don't, I mean, it's this thing, right? So this thing just got added. So I'm pretty sure you don't have to remember this, or you don't have to remember the equation that is forming this. I mean, it would be good if you could remember that, but I guess that is not that important. All you have to do is, for this particular question, all you got to do is, all you got to do is just remember the sequence that car engines, they've got unburned hydrocarbons, they're emitting that. Car engines, the high temperatures in the car engines, the nitrogen and oxygen in the air, they react and they form NO2. And then these two react together to form this PN or PAN. So, and that produces photochemical smog, and it causes breathing problems, all sorts of issues. ठीक है, generally था ना February March में था.
Yeah, it is. It's a question. Question
This
two.
one?
Yeah, it's in this. Question 2. Just go to page 6.
Which is page 6? 5.
Yeah.
And 6.
Last part. D double I.
That's about it, I guess.
Yeah.
Okay. And even the name of that, it's what does the marking scheme say for that? That it's not even, you don't even have to remember the abbreviation. You can just write PAN for this, right?
Yeah, they said PAN or the whatever the.
So it's probably going to be used in a very general way. I mean, they're not going to be very specific with this. I'd say even wait a second, D2. I say we'll do the whole paper now, okay? So just quickly do the paper. First part, oxygen, gas, loses 1 electron, forms a oxygen +1 gas, and that's it. State the general trend in first. What happens across the period? The general trend is it increases. The first ionization energy, and don't write abbreviations, TK, in your paper. It increases. Why does it increase? What's the 3 factors that contribute to
increasing nuclear charge?
Okay, so one of them is increasing nuclear charge. What's the next one?
The shielding is constant.
So you've got constant shielding.
And then greater attraction between outer electrons and the nucleus.
You can also add that the atomic radius gradually decreases. Okay, so your atomic radius gradually decreases, and that's all of these factors, they contribute to an increased attraction. That's the last point. You can make sure you write that point, which is there's more attraction between the nucleus and the outer electron. Explain why the ionization energy A does not allow the general trend in first ionization energy. Why does not follow A? What is A, this one? Why is there a dip at group 6? What are the 2 points?
Repulsion.
The first point would be you're going to talk about the electronic configuration or the difference in electronic configuration. You're going to write that in nitrogen, the electrons are removed from a half-filled p orbital, while in oxygen, the electron is removed from a paired p orbital. That's the first thing. And then you're going to write that there's going to be spin pair repulsion in oxygen, so it is easier to remove electrons. So make sure you describe the electronic configuration. This is a half-filled p orbital. This is a paired p orbital, and there is spin pair repulsion. As the next part, you've got this one, which first thing you have to, it's a period 3 element, right? Which group is this element in?
Group 3.
Yeah, this is it looks like group 3. Is there any other jump? I don't think there's any other jump. It's a gradual increase except for this part. So it's in group 3. So first 3 electrons are removed from the outer shell. So period 3 and group 3. So what element is this? This is aluminum, I guess.
Sir, how big should the jump be for you to figure out that it's like change in shell number?
It should be big enough so that you can clearly see the jump. Like over here, it's around 3,000, around 4,000, I guess 5,000, 3,000. This one is like 8,000, I guess, right? So
Right,
the biggest jump is probably this one. That's it. Okay. So the explanation would be that there's a large increase in ionization energy. Ionization energy between the third and the fourth. So that means the fourth electron is removed from an inner shell, and the outer shell has 3 electrons, so it's in group 3. So this one, Define what a reducing agent is. So what does a reducing agent do?
Gains electrons.
No, it gets oxidized. It loses electrons. It loses electrons and reduces the other substance. Write an equation for Na2O with water that's very, very soluble. So what happens when Na2O reacts with water? NaOH is formed. That's about it. So what is meant by the term amphoteric? That's something that reacts with both acids and bases. Write an equation of Al2O3 with NaOH. It's the same reaction. What is produced? क्या होगा इस केस में? It's going to be
NaLO2
plus H2O. ठीक है. That's the equation. And make sure the equations are balanced. This one is definitely, this one is definitely not balanced. That's 2 NaOH. And I guess now it's balanced.
You could use the other equation here as well, right?
Yeah. The other equation has an extra water in it. I mean, the other equation is Al2O3. There are actually 3, 4, or I mean, they accept a lot of equations for this one. So the other equation, I think, has a water on the left side, and it forms Na AlOH4.
Yeah.
Okay. And you can try and balance this one. 2Al, so it's going to be 2 of this, and there's going to be 2 NaOH. I said next one. Al2O3 is used as a. You can choose anyone. That's now Al2O3. So this time, state the effect of using Al2O3 as a catalyst in the dehydration. Use the Boltzmann distribution to explain your answer. It's going to be the same thing. You're going to use this. That's EA. That's the EA with catalyst, right? Okay. So you've got EA and you've got an activation energy with catalyst. So all you have to do is explain to them that catalyst reduces activation energy. So the number of effective, or the proportion of effective collisions, or the frequency of effective collisions increases because now you have more particles having energy greater than activation energy. What's the structure of P4O6? It's a solid with a melting point of 24. EA with catalyst is lesser than normal. P4O6, what's the type of bonding and structure?
The covalent bonding.
And what's the structure? Giant covalent or simple molecular?
Simple molecular.
So it's going to be simple molecular because it's got low melting points. So it's simple molecular and it's covalent. And you have to explain because it has low melting point. That's what you're going to write. And it hydrolyzes in water as well. Determine the oxidation number of, I mean, that's easy, H3PO3, you can figure it out. It's going to be +3. Next part is the enthalpy change of formation of P4O10 is given. How do you, and you have to figure out the enthalpy of formation. Now, what is the formula if you know the enthalpy of formation of the reactants and also the products? What formula would you use?
Products minus reactants.
Okay, so it's going to be product minus reactants. It's going to be product. So the formula is going to be that the enthalpy of formation of the product, which is P4O10 in this case, minus the enthalpy of formation of the reactants, which is P4O6. In this case, what is the enthalpy of formation of O2, the other reactant?
There is none.
Okay, that's going to be 0. So the enthalpy change of the reaction is basically equal to this because O2 is 0, enthalpy of formation is 0. You already know the enthalpy of reaction, that's minus 1372. 1372. So the enthalpy of formation of P4O10, that's given, that's 3012. And minus this is not given, so you can find what X is. So you can try and calculate X, and that will solve the answer. The other part is you've got P4O10. What type of acid would be formed? ये पिछला clear है?
H3PO3, PO4, sorry.
So it's going to form H3PO4. The next one is we've got the next one is SO2 and SO3 are found in the atmosphere, and that's the one. Construct the equation to show how NO2 is regenerated in this reaction. So how is NO2 regenerated? What does it react with? This is the one. So half oxygen, it forms NO, sorry. It ends up forming NO2 back again. State the product of the reaction that contributes that's PN, right? It's like so that's PN that we did already. Now this one shows how the temperature of the atmosphere varies with height from the ground. So this is the height and this is the temperature. So in the ground it's around 0, and then it drops, increases again, drops again, and then increases again. So the equilibrium reaction in equation 1 has delta HR of -168. Suggest how the position of the equilibrium differs at a height of 20 kilometers compared with a height of 50. So it's just, I mean, it's just a very stupid way of saying that what happens when you change temperature. So you got 20 kilometers, right? So what's happening at 20 kilometers? You got this temperature, right? At 20. What's happening at 50 kilometers? It's this one. So at 50 kilometers, you have, I guess, higher temperature, right? Is that clear? And at 20, you have a lower temperature. Is this clear?
Yes, sir.
Yeah.
So all you have to do now is look at the reaction. Where would the equilibrium shift? Lower temperature, which reaction is favored, exo or endo?
Exo.
Okay, that's going to be exo, and higher temperature, it's going to favor the endo. So we just have to link this with whatever reaction, equation number 1, which I guess is this one. So and they've told us that it's an exothermic reaction. They gave us the value as well, -168. Somewhere they did mention -168. I think over here they already told us that it's -168. So it's going to be exo. The forward is exo and the backward is endo. So we'll come back to this. Endo is the backward one. So over here, the backward reaction would be favored. And exo is the forward one. So in this case, the forward reaction would be favored. And you can talk about the position, equilibrium position moving to the right, and the equilibrium position moving to the left as well. Okay, clear?
Yes, sir.
As I describe and explain the relative reactivity of the halogens down the group when they react with hydrogen to form HCl, HBr, and HI. So how does the reactivity increase down the group? Who's more reactive?
Fluorine.
F2.
Okay, so the reactivity actually decreases down the group. And you've got to explain this as well. So what's the explanation for this? Why are they becoming less reactive?
Decrease in electronegativity.
Okay, so the electronegativity is decreasing. That means they are less interested in electrons, and you can explain that further as well. That why is the electronegativity decreasing? Because again, we're not sure, so we should answer this as fully as possible. So the electronegativity decreases. Iodine doesn't really like to gain electrons. Why doesn't it like to gain electrons?
Because of more shielding and less attraction between the nucleus and valence electrons.
Okay, so you can just go with more shielding. The shielding effect increases down the group, so so less attraction for electrons. Now HCl is a product of several different reactions. What happens when SiCl4 is added to water?
SiOH4 is formed.
Okay, SiOH4 or SiO2 and HCl, right? And balance this. So you get vigorous hydrolysis. And then you have this reaction. In reaction 2, NaCl reacts with concentrated H2SO4 to form HCl and NaHSO4. So what is the type of reaction that's happening?
Is it
Acid
redox?
base?
Okay, you can write it as acid base or a displacement reaction as well. TK, the last time I saw this, both were acceptable, but not sure. This is the latest one. Check. It's definitely an acid-base reaction.
Displacement is only allowed for one of those boxes. That's what it says in the mark scheme.
Okay, but this is displacement. I mean, there's more of displacement happening over here, right? So that's the latest one. I mean, it is displacement, TK, so displacement is also fine. What just happens is that Cl-1 doesn't really like to lose electrons. So what happens is that in the solution, you've got Na+1, you've got Cl-1. Cl-1 is an atom that really likes to attract electrons. So it doesn't really like to lose electrons. So what happens is that the ions, they just mix up, and these H+1 and Cl ions, they might get together to form HCl gas, which would form fumes. So that's just displacement. No redox reaction happens. But when you move down the group, what happens? Br-1 likes to lose electrons. So that's what this. So Br-1 turns into Br2, and the sulfur gets reduced to sulfur dioxide. So it's obviously a redox reaction. And why does this happen? Why does this happen? Because down the group, the halides become stronger. They become stronger reducing agent. So stronger reducing agents down the group. So they lose electrons easily. Is that clear?
Yes, sir.
So if you had NaI, the redox reaction would be even stronger. Now, when heated with a Bunsen burner, HCl does not decompose, HI does. So what's the difference between HCl and HI? Why is HI decomposing?
HCl has stronger bonds.
Yeah, so it's got a higher bond energy or stronger bonds, and why?
It's less shielded.
Yeah, that would be acceptable, but stronger bonds because you've got shorter bond length.
More orbital overlap.
And that leads to
the ignore bond length. The MS, it said ignore bond length.
They did talk about orbital overlap. What was the other point for?
There was just one point. It was the HCl bond is stronger.
So that's one mark. Well, that's why if it was a 2 mark, then they would probably not ignore that, right?
Yeah. So they ignored it because it's just 1 mark. Doesn't.
Yeah, because it's just 1 mark, so you don't have to explain that fully. Like,
all right.
Not because it was wrong or something. So yeah, state what is meant by the term Brocellari acid. That's a proton donor. That's it. And strong, what does strong mean? It fully ionizes. You've got to sketch titration curves. The first thing is just figure out NaOH is being added to HBr, right? So you've got HBr at the bottom. And you're adding NaOH from the top. So इसमें मुझे बताओ कि what will happen that initially what would be the pH?
1.
I mean, let's make it 2. I mean, 1 would be but 1 is fine as well. Okay, let's make it 2. In both cases, it's this same thing. You've got in the second one, you're adding NH3 from the top. And the HBr is at the bottom. So your starting pH would be somewhere around 1 and 2, right? When will the HBr get neutralized? What is the volume of NOH at which the pH would become 7? So how many moles of HBr do you have? That's 2.5 times 10 power minus 3 moles, right?
Yes.
So HBr and NaOH react in 1:1. So if you have 2.5 times 10 power minus 3 moles, there should be 2.5 times 10 power minus 3 moles of NaOH that should be added. So the volume should be 25 cm cube, right? For NaOH.
Yes.
Okay, that will give you the same moles, 25 into 0.1 divided by 1000. So at 25, in both cases, it's 1:1. I mean, you can construct the equation, but in both cases, NH3 and HBr, that's 1:1. NaOH with HBr, that's also 1:1. So in both cases, you've got 1:1. So the neutralization will happen at 25. At 25, the pH will be around 7, right?
Yes.
But then you're not just adding 25 cm cube, you're adding 45 cm cube. So 45 cm cube is excess NaOH being added. So all the HBr has reacted and you're adding too much NaOH. So the solution will then eventually turn basic, very strongly basic in the case of NaOH. Is that clear? So when you add 45, you've added too much of it. The acid is already gone. So you're adding just base into this flask and that's going to make it very, very basic. What will be the final pH of this one at 45?
10.
11.
Okay. 10, I guess, would be a better choice. 11 would be fine as well, as long as it's not too basic, because NH3, remember, is a weak base. And remember the curve, maximum, around the equivalence point, that's the curve is going to be almost vertical. Actually, it's going to be vertical. It's got to be vertical, right? And then very gradual change initially. And remember, it should be curved, like it should slightly curved. And that's this one, right? No, I mean, you have to be clear, like it's obviously a strong acid. So you have to be clear with this, that 2 and 1 would be fine. 3 is like, I mean, it's borderline. So you have to show that it's a strong acid. And that's how your curves would look like. The only thing that you have to be worried about is, where's the equivalence point? When should the pH be 7? When's the turning point? When does the pH change from acidic to basic?
To find that by calculations, yeah?
Yeah, you have to do moles, right? And you have to write the equation. In this case, we didn't write the equation, but I mean, you should know that it's sometimes it's not 1:1. Like if you had, let's say, H2SO4 as the acid, right? Then you would have to do a bit more calculations to figure out the equivalence point. Like let's say I had a question that it was 25 cm cube, 0.1 mole per dm cube, mole per dm cube H2SO4, and they were adding 0.1 mole per dm cube NaOH, H2SO4, sorry. Now this one is clearly not 1:1 because the NaOH, how many moles is this? This is 2.5 times 10 power minus 3 moles, right? The NaOH, it's going to be 2:1 now. Because if you write the whole balanced equation, it's going to be Na2SO4 plus 2H2O, right? So the moles of NaOH must be double the amount. It should be 5 times 10 power minus 3 moles. Is that clear? And you can only get 5 times 10 power minus 3 moles if you add 50 cm cube of it. So you would have to, like, it won't even get neutralized in this graph. Is that clear?
Yes.
I mean, you can't even show it on the graph because you're just adding 45 cm cube. So if this is 0.1 mole per dm cube, then the amount of NaOH for neutralization would be, or equivalence would be 50 cm cube. that's when you're going to get 5 times 10 power minus 3 moles. So remember the equivalence point, you can definitely use C1 V1 is equal to C2 V2. But remember C1 V1 is equal to C2 V2 can only be used if the ratio is 1:1. Like you can't use it if it's 1:2. Remember, you can't use that 1:2. So do the moles question. Finally, we'll do this. This is electrophilic addition. You've got remember the arrows, curly arrow, positive. You got electrons over here, and these electrons would be repelled. It's going to form a carbocation. Where will the H get attached? This one or this one?
The right one.
Right one.
Okay, so the carbocation would be that the right one will have 3 H's, Markovnikov's rule, and this one has 3 H's. It had 1 H, and that will turn into a carbocation. And then the next step, you had a Br-1, and that Br-1 with its electrons is going to come in, and it's going to bond with this, and it's going to form the final product. So draw the final product. Explain why 2 bromoalkanes are not produced in equal amounts. Why is it on the right one? What's the explanation for this?
It produces a more stable second degree carbocation.
Okay, but remember, you've given too many lines. So you'll write the Markovnikov's rule that H likes to bond with the carbon in the double bond with more H atoms. Why? Because a second degree carbocation is more stable. Why is it stable? Because it's got more electron donating alkyl chains. Okay, so I'm going to state the Markovnikov's rule as well in your answer. Is that clear?
Yes.
So this is your 2 degree carbocation that's more stable because it's got 2 electron donating alkyl chains. The reaction of this thing with NaOH, that's nucleophilic substitution, is different depending on whether water or ethanol is used. Identify the organic and inorganic products of the reaction. What happens if you in each solvent? In case of aqueous, what will happen in aqueous? The Br will get substituted, right?
Yes.
So what are the 2 products that are going to be produced? Alcohol? Okay, that's going to be propanol. So it's going to be CH3, CH2. What is the inorganic product that's going to be produced?
NABR.
Okay, that's going to be NABR. The Br will leave and there's Na. So you'll have NABR probably in aqueous state. In ethanolic, what happens in ethanolic? Okay, halogenoalkane in ethanolic, that results in elimination, right? It forms an alkene. So in ethanolic, what will happen? The Br would be gone, and the H from the neighboring atom would be gone. So it's going to form propene, right? Clear?
Yes.
And what is going to be produced? What's the inorganic product that's going to be produced?
HBr.
Yeah, that's going to be HBr. The Br and H are going to leave and they're going to form HBr. So next one, quickly, we've got this. Haji.
So for the previous question, it said NABR and H2O for the reaction with ethanol as the inorganic product.
With ethanol?
Yeah, in the marking scheme, it said NABR plus H2O.
Yeah, sir. Wouldn't the Na react with the Br, and then there's an hydrogen as well?
No, 1 second. They're talking about this one, right?
The ethanol one, yeah.
It's definitely HBr.
Sure. Then what happens to the Na from the NaOH?
The NaOH never ionizes in ethanol. So it stays like NaOH doesn't ionize in ethanol. I mean, definitely, it's HBr. It should not be. It should not be.
There's no except HBr as an answer.
Maybe there might be an error over there, but it has to be HBr. ठीक है वो एक second, let me. I mean, the book has HBr. Let me just check somewhere. This one, they've actually, this one, this is authentic. Okay, it's going to be NaBrH2O. Not sure why the book has HBr. Okay, so that is correct. The marking scheme is correct. Is that clear?
Sir, but can you explain why?
I mean, I guess it's the same thing that HBr is formed, but the HBr is acidic, and that HBr ends up reacting. I mean, HBr is an acid, right? Like HCl.
Yes.
So that HBr ends up reacting with NaOH, and it forms a salt and a water molecule. So that's what's happening.
Oh, okay. Understood.
Okay. So this is fine. I guess the book was wrong. So, but the HBr is formed, except that the HBr gets, so over here they're assuming that it reacts with NaOH and ends up forming salt and a water molecule. So where's the paper? So this part is wrong. So it's NaBr plus H2O for this. I said next one, we've got, let's do this one. We've got a completed table to state what you would observe when J reacts with the reagents. 2,4-D and pH, what will happen?
Orange, yellow, PP2.
Okay, orange precipitate. Tolerance, what will happen? Will it react?
Yes.
Silver mirror.
Okay, silver mirror. Sodium metal, will this react?
Yes, bubbling.
Yes.
Okay, the alcohol will react. So you'll have bubbles or bubbles of H2 gas. J has two optical isomers. Draw the three-dimensional. So this one is chiral, so you just have to draw. I said, remember, it doesn't really matter which bond is drawn in which direction. Okay, so you got OH and CHO and CH3. CHO and CH3. And on that side, I think you had CO. And I guess another CH3. So you'll just draw an exact mirrored version for this. See, so there's going to be an exact mirrored version for this. This one, K is used to make an addition polymer perspex. What is reaction number 1?
Esterification.
Carboxylic acid. So state the conditions required for esterification.
Concentrated H2SO4.
The conditions are
reflux.
And heat with reflux, right? Identify L. What is L? What is the molecule that got added over here?
Methanol.
Which one?
Methanol.
Because that's methanol because it's one carbon atom, right? So that's methanol, one repeat unit of the addition polymer. So what is the repeat unit? It's just you had the double bond, but the double bond would so you had the double bond, but the double bond would go away, and you'll have N in its place. So yeah. So that's your repeat unit. Use information suggests how the infrared spectra of M and perspex would differ. So M and this, what is the only difference between them?
Carbon double bond.
It's just the double bond, right? That's the only difference. Otherwise, every other bond is the same. So you just look at the data booklet. Go and have a look at the double bond. So this absorption will not be there. 1500 to 1680, the one with alkene double bond. That is the 1580, 1600. That is no longer going to be there. They actually gave you a table next to it. As I move into the next one, we've got complete the table 4.3 to identify the reagents used and the type of reaction. So what's the first one? Step number 1.
HCN and KCN.
Okay, so the reagent is HCN with trace amounts of or NaCN as a catalyst.
If we write like in NaCN, was it wrong? Or is it wrong?
If you just write NaCN?
No, in, like HCN in NaCN.
It's not in NaCN, it's just that there's some amount of NaCN that's added to speed up the reaction, that's it.
All right.
I mean, they're probably accepted. I mean, it's just, kind of acceptable, but it's HCN and NaCN as the catalyst. What is the type of reaction, this one?
Nucleophilic addition.
Yeah, that's nucleophilic addition. CN turning into COH. What's happening here?
Acid hydrolysis.
Yeah, that's acid hydrolysis. So dilute acid like HCl. Plus reflux. And then finally this thing turning into this one. What is happening here?
Dehydration.
So the OH is lost. One of the H's are lost and they form a double bond over here. So what is the type of, that's dehydration, right? So
sir, in the first reaction, there's also an OH bond forming in the step 1.
This ke andar hota hai na, when you have nucleophilic addition, this one. Where's nucleophilic addition? So when you have nucleophilic addition, a ketone, right? The CN-1 attacks from the middle, from the bottom, gets attracted to the carbon. CN joins with the carbon, or jo upar O hota na, that ends up forming with bonding with H+1, and it ends up forming OH. ठीक है, clear?
Yes, sir. Sir, one more thing. Can you give any tip like to manage the time? Anything important?
Time का बस ये कि time का बताऊँ क्या करना है, time का ये कि you get stuck on any question, ठीक है? Just move on very quickly, ठीक है? Just don't panic on that. Continue to move forward, ठीक है? And just do the ones. There's going to be at least 1 or 2 parts where you're going to get stuck. ठीक है? And you will probably वो शुरू में भी आ सकता है, end में भी आ सकता है. It could be anywhere, but there's at least going to be 1 or 2, like 3-4 marks where you are going to get stuck. So just keep that right at the end. First priority is try to do the whole paper as quickly as possible. Okay? And
do you suggest solving organic questions first before the others?
If you can do it quickly, solve any question that you can do quickly. Try to solve the maximum paper as quickly as possible. That's the first strategy.
Okay.
And then you can sort of in the next attempt, take the second and do the ones. Like for example, I'll just give you an idea. For example, if this is the paper, right? I'll probably leave the calculation questions at the end. Like I'll skip those. Like it's a lot quicker to do the inorganic questions because like straightforward, you can just do it. I mean, for example, all these equations, I'll probably attempt those first, and I mean this one, I might leave till the end. The calculations I'll do at the end. That's how I'll go. Even this one, I'll probably leave it at the end and move on and do the rest first. Because these are very straightforward. You can just answer them directly. You don't have to do any calculation. You don't have to think because you need time for this one. Like this question over here, it needs time. You need to first. I mean, you can't do this quickly. The problem with this question, you can't really do this if you're just speeding up. You have to sort of, because you're going to make silly mistakes with this one. So you have to sort of wait and you have to think. So try and do the ones, the others as quickly as possible, and then sort of spend time on this one. And even though it's just 1 mark, you're going to waste a lot of time for this 1 mark question. Look at the mark as well. Like so keep those questions at the end. I mean, that's one strategy you should follow, but it's up to you, TK, whatever suits you.
Okay, sir.
Any other advice or encouragement? Any other pieces?
Just don't panic anyway. It's just remember, keep this in mind that the paper could be very easy. The paper could be very hard as well. I mean, there have been papers that are extremely hard as well. So if you get a very, if you get a very difficult paper, just don't panic. Like focus on the questions that you're able to solve and do them as quickly as possible. क्योंकि बहुत सारा ना panic के अंदर issue आता है कि you just like if you're stuck on the first question and then all of a sudden you start panicking. ठीक है, just try to quickly do as many as you can and then focus on the ones that are tough. And you'll know if you've practiced a lot of questions, you'll know that it's a tough paper. So if it's a tough paper, then it's a tough paper for everyone. Then, but if it's an easy paper, you'll know it's an easy paper. ठीक है. So बाकी है कि वो pencil और pen करना, just be careful. Try to do it in pen and show the working. Like even if you want to write this, show this. Don't assume that the examiner knows, because even in this question, you'll make silly mistakes on your calculator. What might happen is you might get one thing wrong, or maybe do something wrong on the calculator, and you'll make a mistake, and maybe your answer is coming out to be wrong. But if you have written it properly and you have all your steps, all your working, everything is clear, the examiner would know that you messed up somewhere in the calculator and you pretty much did everything right. So maybe they will give you that 1 mark as well. So it's kind of working, and make sure you, especially with calculations, make sure you show all the working. Okay, clear?
Yes, sir.
Yes, sir.
And just revise now. I guess you just revise inorganic, you revise organic. Okay, I mean, just don't focus on the papers now. Just go through inorganic, organic, a bit of atomic structure, like ionization energy questions, because they're very typical questions. They come very frequently. And maybe do a few moles questions. That's going to be troubling. Like if you get a big moles question, that's going to be time wasting. That's going to waste a lot of your time if you get a big moles question, like a 10 or 12 mark question. So be careful with that. So try and attempt, like in the last seconds, just go through inorganic, organic, and maybe do a few big moles questions. Okay?
Yes.
Okay, sir.
Okay, sir.
Okay.
Thank you.
Okay, sir.
Best
Thank
of luck.
you.
Allah Hafiz.
Allah Hafiz.